Hello, welcome to this YouTube channel. Today I'll be discussing how to analyze the docking scores you've obtained from molecular docking. Now, in previous videos, I've shown you how to carry out molecular docking, and today we will see what we can do with the results we obtain from that process. Now, the first thing to understand is that a docking score is simply your first clue, not your final answer. Now, for a lot of people, once they've carried out molecular docking and they obtain values, maybe -5, -6 kilocalories per mole, they simply feel they've done everything. But that's not true. A docking score just gives you an inkling into what you're supposed to analyze. Now, the first thing we need to do is to understand what a docking score is. Now, the docking score is a numerical estimate of the binding between a macromolecule, which is your target macromolecule, your target protein, and then a small molecule, which is often called a ligand. Now, the estimate in numbers of that interaction is what is often given as docking score. Now, if you use AutoDock, you observe that it gives the docking score in terms of kilocalories per mole, and you see it as binding affinity. Other algorithms will give different kind of docking scores. You will see mole dock, GDock, and many other things. But it's important to recognize that the more negative the docking score, the greater the interaction between those two molecules. That is the macromolecule you are working with and then your ligand. Now, so generally, now there are times when the more negative doesn't really translate to stronger binding, but generally, we often take it that once you have more negative values, it shows that there is a strong interaction between the molecules you are working with. Now, it's also important to understand that while the docking score might just be a value, maybe -8.5, -7.3, -2, that value captures different energy components. Now, those energy components are obtained from the interactions between your macromolecule and your ligand. Now, some of those interactions are hydrogen bonding, hydrophobic interactions like pi-pi interactions, pi-stack interactions, and other interactions, van der Waals interactions, which are weak interactions between molecules of your atoms of your macromolecule and that of your ligand. We can also have electrostatic interactions between the charged part of the macromolecule you are working with, a protein, and then that of your ligand. So that value you see as a docking score captures all of these interactions. Now, if you are using AutoDock, you observe that it gives you just a single value, and it's very difficult to actually break that single value into these components. But there are softwares like if you are using Molecular Virtual Docker, it tells you the contribution of each interaction to the docking score you obtain, and that helps a lot. But understand that once you've gotten a docking score, it's likely that it's capturing all of these interactions. Now, the next thing to understand is how you can interpret the results you've gotten. Now, like I told you, the more negative the value, the more likely that you have a strong interaction. I'll put it that way. Now, so when you have, just on a general note, when you have values that are less than -10 kilocalories per mole, it shows that you are having strong interactions between those two molecules. Yes, strong interactions. So when you're having binding values, docking scores around -10, -11, -11.2, -12, -13, it suggests strong interactions. Now, but when you have values between -7 to -9, that suggests moderate interactions. Now we are talking about a general perspective. Now, having values that are greater than minus 6, that is minus 6, minus 5, minus 4, minus 2, it shows that the interaction between those two molecules are weak interactions, most likely. So it's important you note this. Now, but beyond that, don't just look at the values you've gotten. It's important that you compare the scores you've gotten with the ligands you are working with. What do I mean? Look at this. I want to give you a practical comparison. So we have compounds M2, M3, M4. We have that of the standard drug, and we have a co-crystallized ligand. Now you can see the docking scores. Now, looking at this result, you can see that M3 has um, the best docking score, minus 8.4, because it's higher than every other. Sorry, yes, higher in that sense. It's more negative than every other docking score we have here, followed by M2. Now, so in discussing this kind of result, we would assume that M3 would have a strong interaction with the target protein, and that interaction should be stronger than that of M2 and then that of M4. Now, you observe that for the standard drug used for that study, it's minus 8.1. So M3 and yes, M3 shows a higher docking score than the standard drug, and then even the co-crystallized ligand, which is often used as a standard. So remember that the more negative the value, the more likely you have stronger interactions. Now, once you have values that are very close, minus 8.1 and minus 8.0, it means that the interaction between those molecules and then the target protein is not so far from each other. Now, I would also tell you that sometimes docking scores can be misleading. Yes, sometimes docking score. So it's possible that you are docking in the wrong cavity. You are docking in the wrong um, part of your protein, and then you will get an unusual high score. Now, even if that score is high, it means that your docking score is not reliable, and that's why you should refer to the videos I've done. I've always shown you how you can get the dimensions of the active site. Remember, just docking alone is not enough. You must be docking within the active site of that macromolecule. Now, you also find out that there are ligands that score very well, but their in vitro activity is so low, they don't bind well in vitro. So that's another issue when docking scores can be misleading. Now, the third situation where you can have misleading docking scores is when you have tools that do not capture entropy, that do not capture the water molecules, that do not even capture the protein flexibility, and then they just give you scores. Now, while those scores are simply good, you will find out that they are not reliable, especially when you carry out the in vitro part of the work. Now, so in cases when you cannot trust your docking scores, and if you've done docking a lot, you would observe that you will run into those cases. What are you supposed to do? It's important that you use molecular dynamics, or you can use visual inspection to validate what you've done. Now, visual inspection, so you can check if that interaction is occurring within the active site. Now, I want to give you some examples of molecules that were found to be very active when they were docked, but when it was the experiment were carried out in vitro, they were found out to be inactive. So we have a case reported by Dibetal in 2024 where he had 1,2-dihydropyridine derivatives. They showed excellent docking scores, but their in vitro activity was quite poor. And the reason for that was due to ADME properties, that is absorption, distribution, metabolism, and excretion. So if those molecules have good docking scores, but they are not well absorbed in the body, or they are not well distributed, or they have issues with metabolism and even excretion, then it's possible that they will not have good in vitro activity. And that's why it's not just enough to carry out docking. It's also important that you carry out ADME um, tests to look at the druggability or the drug likeness of the molecules you are working with. Now, we also found out that Ali et al. In 2023 also carried out um, molecular docking and got excellent docking results. But due to issues of solubility, stability, permeability, those synthetic compounds we have found to not have the expected antidiabetic activity because it was targeting alpha glucosidase. So it's not just enough to get good docking scores. Are those compounds soluble? Will they be soluble in the environment they will be working with? Are they stable once they get into the bodies living um, of living things or in the body of humans? Will they be stable? Will they not degrade before getting to the active site? These are questions you should ask. Also, are they permeable? Can they pass through the lipid layer that you will find in the bodies of living organisms? So it's important that you consider this. So before even carrying out molecular docking, it's important that you carry out ADME test. That is to test for the absorption, distribution, metabolism, and excretion. Now, we also found a case where some compounds, some pyrimidine heterocycles showed excellent docking scores towards anti-cancer activity. However, they were found to be inactive, and this was blamed on bioavailability. Now, that means that even though that compound might be active, it's not available in the right concentration at that active site. It's possible that before getting there, it degrades or it metabolizes. So these are things that can be captured by your ADME test. So there are times when you can carry out docking and then you get excellent docking scores. But when you carry out the experiment in vitro, you get results that are just opposite what you got. And that's due to a lot of times that is due to poor ADME properties. Now, what are some of the things you can do when you are carrying out molecular docking and you're working with docking scores? Always visualize the binding mode. So don't just rely on the result you've gotten. No, visualize it. It's important you check if it's that interaction is taking place in the active site. Secondly, it's important that you check if you're having interactions like hydrogen bond interactions, hydrophobic interactions, and interactions with active site residues. Now, let me show you an example of how to do that. Now, so look at I showed you a result. Okay, M2, M3, and M4. So I have now you can see that this is the target protein 8B07. That's the label for it, or sorry, the code. And then these are different binding poses. So you have M2, we have 10 binding poses, the same thing for M3, M4. So it's important we check if this is occurring in the right cavity. So I want to see if this can, okay, 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 good. So now this is good. So we can see, okay, so we can see the molecules we have in this cavity. So you can find that, you can see that. Now, so let's use this. Okay, wow, that's good. Now, what you want to do apart from this is to visualize if you can have hydrogen interaction, hydrogen bond interactions, hydrophobic interactions. So I want to visualize that. So click on this and then click on this and then let us show a 2D diagram to see if those interactions occur. Wow, that's interesting. So we can see that we have those interactions. We have hydrogen bond interactions green. We have van der Waal interactions. You can see them: serine 141, leucine 159. We also have pi sigma interaction, pi pi T shaped interactions. These are hydrophobic interactions. We also even have halogen interactions. Now, these are interactions, especially if you are sure it is within the active site, tells you that your results are reliable. Now, this is for M2, I suppose. Now, let's see M2 minus 8.0. So you can see the interaction. So we have different interactions: hydrophobic interactions, hydrogen bonding. We also have halogen interactions, as well as van der Waal interactions. Now let's see M3. Let's see M3. Now you see that M3 is also within that same cavity. So let's check this. So this is M3. Wow, it's within that same cavity. So click on it, and then let's see the interaction. Okay, cool. Now, so we can see different interactions. We also find van der Waal interactions. We find pi sigma interaction. You can see it with valine. And then the localized electrons for the benzene ring. And then you can see halogen interactions, carbon hydrogen interactions. So we can see both hydrogen bond interaction, hydrophobic interactions, and even van der Waal interactions. Now let's see M4. So let's see M4. Okay, M4 also. Now you observe I'm clicking model 2. If you click the first one, it will not select it. So it will not select. So click the second. Now you can see it now, and then let me select it here, and then let's see the interactions. Okay, good. So we find out that now if you see something for M4, we had lesser interactions. Now, so these are the interactions we have. So we have lesser interactions compared to M3 and M2. So let's see if our scores reflect that. So you can see that, so because we had lesser interactions and maybe the interactions are not even that strong, now it's giving us a lower docking score. While M2 and M3, they had a lot of interactions and possibly strong interactions. Now, to consider how strong the interaction might be, you also have to obtain the distance. Yes, you can obtain the distance between your the atom and then the amino acid, and then that distance, if it's it gives you a measure of how strong that interaction might be. So we can see that M2 and M3 had more interactions, and I believe more stronger interactions when compared to M4. Yes, when compared to M4. And in fact, here you can see that we don't even have a lot of hydrophobic interactions. We don't have halogen interactions, and all those interactions contribute to the docking score. So it's important that when you want to interpret your result, it's not just enough to interpret, oh, I got minus 8.0, I got minus 8.4. It's important you also visualize that interaction and see the different interactions that are responsible for the scores you've gotten. So that's is important. So make sure you visualize the binding mode, and then don't just rely on it. Check this, and then I've showed you how you can do that. Those interactions are very important in explaining your results. Now, um, in conclusion, it's important to note that when you get a lower docking score, it does not necessarily mean that you have stronger binding. No, it's important that you interpret it based on the system you are working with, because you can get into situations where you have very low, I mean, docking scores minus 11, minus 12, very low docking scores, and you think it will give you stronger binding. But when you now carry out the in vitro work, you now discover that there are a lot of factors that are responsible for the negative result you are getting. So it's important that you interpret it within the context of the system you are working with. Secondly, make sure you are docking within the active site. This cannot be overemphasized. Make sure you are docking within the active site. And then if you have issues trusting your result, why not carry out a visual um, why not carry out a visualization of that interaction? Don't just rely on a score. Now, thank you for listening. Bye bye.